Welcome everyone to today's lecture on potentiometry, a key technique in pharmaceutical analysis. This method allows us to determine the concentration of a solute in a solution by measuring the potential difference between two electrodes. I'll be guiding you through the principles, equipment, and applications. But in this video, we're only going to look about the principles and definition of some terms and the Nast equation. Potentiometry is a branch of electroanalytical chemistry focused on measuring potential without any current flow. The core setup involves an electrochemical cell with two solutions connected with a salt bridge and electrodes. As you can see in the diagram in the figure 1 on your screen, this setup allows us to measure potential created by the movement of ions between the electrodes. Electrochemistry is a part of chemistry which determines electrochemical properties of substance. An electric circuit is required for measuring current. The unit for current is amp. And potential also, the voltage, that means the unit for potential is voltage, created by movement of charged particles. Galvanic cell, that is the electrochemical cell as in the figure, serves as an example of such system. Three distinct charge transfer processes are described for the system in figure 1. Electrons move in electrodes and wires from zinc electrode to copper electrode. Ions move in solution. In solution on the left, zinc ions move away from the electrode and sulfate ions move towards it. In solution on the right, copper ions move towards the electrode and negative charged ions, that is the sulfate, away from it. In salt bridge, positive ions move right and negative ions move left. On the surface of the electrodes, electrons are transferred to ions or vice versa. The zinc electrode dissolves. The metallic copper is decomposed on the electrode surface. In potentiometry, we measure the concentration of solutes by determining the potential difference between two electrodes with no current flow. This method is highly sensitive and is used to gauge the concentration of analyte in various solutions. Electrode potential is the tendency of an electrode to lose or gain electrons. This concept is central to understanding how potentiometric measurements work, as the potential difference between electrodes reflects the concentration of ions in the solution. The standard electrode potential, E0, is the potential of a metal electrode when it is placed in a 1 molar solution of its own ions at a temperature of 25 degrees Celsius. This value is used as a reference point to compare the reactivity of different metals. The standard potential can help predict whether a metal will be oxidized or reduced when it comes in contact with another substance. Oxidation potential refers to the tendency of a substance to lose electrons and thereby get oxidized. It is the potential required to remove electrons from an atom or ions in electrochemical terms. A higher oxidation potential indicates a greater tendency for the substance to lose electrons and undergo oxidation. Reduction potential is the opposite of oxidation potential. It measures the tendency of a substance to gain electrons and thereby get reduced. A higher reduction potential indicates a greater likelihood that the substance will accept electrons and undergo reduction. Well, in electrochemical cell, substances with high reduction potential are often the ones that get reduced. Potentiometer, an instrument which can measure the potential developed without drawing any current. In simple form, consists of two electrical circuits in combination. Measured potential can be used to determine the quantity of analyte in terms of concentration. The principle behind potentiometry is that when a pair of electrodes is placed in a solution, the potential difference changes as the concentration of ions changes. This is often observed during titration, where the potential shifts as the analyte reacts with the titrants. The principle the principle is that there are two indicators are used. The reference electrode, which maintains the constant potential, and the indicator electrode, which indicates a potential change. There is a solution must be stirred during titration. Now, during this titration, active ingredient being determined produces an electric potential with a suitable indicator electrode. The titration is followed by the fall in potential as the ingredient is used up, is used up by the titrant. That is, I will say the titrant may cause production of potential at the end point when titrant is no longer being used up by the active ingredient. The sudden increase in titrant concentration results in sudden increase of potential. The endpoint is determined by a sudden change in potential. From the endpoint determination, the concentration of active ingredient can be measured. It is a regular titration, but instead of the indicator, we use potentiometer. It measures, one of the principles is that it measures the change in potential. It can be used in all kinds of titration like acid-base titration, redox titration, complexometry as well. Based on potential measurement of electrochemical cell without any appreciable current. The use of electrodes to measure voltage from chemical reaction. A typical potentiometric cell consists of reference electrode, an indicator electrode, a salt bridge, as you can see in the diagram. The potential of these components as shown by the equation. Reference electrode, EREF, is a half cell having a known potential that remains constant at constant temperature and independent of the composition of the analyte solution, e.g. like the caramel electrode and silver chloride electrode. An indicator electrode has a potential that varies with variation in the concentration of an analyte. Most indicator electrodes used in potentiometry are selective in their response. Metallic indicator electrode and membrane electrodes are types of indicator electrodes. The third component of a potentiometric cell is a salt bridge, which is used to prevent the interference of the analyte solution with the reference solution. The analyte solution is a sample solution whose potential is to be measured. The indicator electrode is the electrode which responds to the change in the potential of the analyte. The electromotive force of the complete cell is given by the following equation. E cell equals to E reference plus E indicator plus E junction. E reference is the electromotive force of the reference electrode. E indicator electromotive force of the indicator electrode. E junction is the indicator electrode and is the electromotive force of the junction of the liquid. The unit for the potential are millivolts, denoted by MV. The potential develops across the liquid junction at each end of the salt bridge. The junction potential across the salt bridge EJ is small, so small that it can be neglected. The reference electrode, such as example of it is the standard hydrogen electrode, the silver chloride electrode, have a known and stable potential. They are crucial for providing a stable point of comparison in potentiometric measurement. The reference electrode is the electrode which consists of its own potential value, and it is stable when dipped into the sample solution. While the indicator electrode has an unknown potential, it is immersed in the analyzed solution. The potential is directly proportional to the ion concentration, and its potential is sensitive to the concentration of the analyte. Example of indicator electrode is the metal electrode, the ion selective electrode. Let's talk a little bit about this electromotive force of the cell, of the complete electrochemical cell. Now, the electromotive force of the chemical cell is the total voltage generated by the cell. This voltage is the sum of the potential contributed by the various components of the cell, like the E reference, the E indicator, and the E junction. The E junction is the E salt bridge. The E reference, the electromotive force of the reference electrode, is stable, as said earlier, and has a known potential used as a baseline to measure the potential of the indicator electrode. That is why it's called the reference electrode. The electromotive force of the indicator electrode. The indicator electrode is one of where the reaction of interest takes place. Its potential changes depending on the concentration of the species involved in the reaction. The salt bridge, the electromotive force of the salt bridge connects the two half cells of the electrochemical cell. The salt bridge minimizes the liquid junction potential. The liquid junction potential is the voltage difference that can occur when two different solutions come into contact and complete the circuit. The summary of the equation is the overall cell EMF of the cell is the sum of the potential from E reference, that is a constant value, E indicator, the indicator electrode, which varies based on the reaction, the salt bridge, which typically has a small, often negligible value, but is included for accuracy. This equation is fundamental in potentiometry and other electrochemical techniques, where the goal is to measure the EMF to gain insight into the concentration of ions in a solution or the progress of a chemical reaction. A salt bridge is a crucial component in an electrochemical cell, serving several important functions to ensure the proper operation of the cell. The function of the salt bridge is to maintain one of the functions. Let's explain few of these functions in details. When we say it maintains electrical neutrality. Now, during the redox reaction in the electrochemical cell, one half cell may accumulate positive ions, that is cations, while the other accumulates the negative ions, that is the anions. This imbalance in charge can stop the reaction by creating an electrical potential that opposes both electron flow. The salt bridge allows the migration of ions to maintain electrical neutrality in each half cell, enabling the redox reaction to continue. Yes. Now, when we say it prevents solution mixing, direct mixing of the solution from the two half cells could lead to unwanted side reactions that can interfere with the primary reaction of interest. So now the salt bridge physically separates the solution while allowing ionic conduction, thus preventing these side reactions. When we say that one of the functions is it reduces liquid junction potential. Now, when two different solutions come into contact, a small voltage difference known as the liquid junction potential can develop due to differences in ion mobility. The salt bridge helps to minimize this potential by providing a pathway with ions that have similar mobility, thus ensuring a more stable and accurate measurement of the cell's electromotive force. Now, when we say how the salt bridge, how does it work? You see, in an electrochemical cell, oxidation occurs in one half cell, producing electrons and positive ions, right? Now, the electrons flow through the external circuit to the other half cell, where reduction occurs. The positive ion is in the oxidation half cell, migrate towards the salt bridge, while negative ions from the salt bridge migrate into the reduction half cell. This ion exchange through the salt bridge keeps both solutions electrically neutral and prevents charge buildup that could halt the reaction. Now, the most common salt bridge electrolytes are used that does not react with other chemical in the cell are potassium chloride, because they have potassium and chloride ions have similar mobility, which helps in reducing the liquid junction potential. The potassium nitrate is also another common electrolyte used in the salt bridge. Now, the importance, no matter, even though it is negligible, the salt bridge is very important. Now, without the salt bridge, the electrochemical cell would quickly reach a point where the reaction could no longer proceed due to a lot of charge build-up. The salt bridge thus plays a vital role in sustaining the flow of electrons and the overall function of the cell. In this diagram, you can see the potentiometer, the cations and the anions, the salt bridge, the solution, oxidation, the reduction, the migration of ions from the salt bridge also. The theory described relates to the fundamental principle of potentiometry, which involves measuring the potential of the electrochemical cell to determine the concentration of analyte in a solution, as I said earlier. The core of this theory is the Nast equation, which is used to relate the potential of an electrochemical cell to the concentration of the ions involved in the reaction. Here is the breakdown of each term in the reaction. The E is the electrode potential of the solution. This is the actual potential, that is the voltage, measured by the electrode when it is immersed in the sample solution. It is dependent on the concentration of ions in the solution and the condition of the system. The E0 is the standard electrode potential. This is the potential of the electrode when it is in standard state, meaning it is in a solution where the ion concentration are 1 molar and the temperature is 25 degrees Celsius. The standard electrode potential is a known value for specific electron and serve as a reference point. The gas constant, R, is 8.314 joules per mole Kelvin. This is a physical constant that relates energy scale to temperature and is used in many equations in chemistry and physics. T, we all know, is temperature, which is measured in Kelvin. The temperature at which the measurement is taken is measured. Temperature affects the movement of ions, in solution, and therefore it affects the potential difference. The number N, the number of electron transfer. A redox reaction occurring at the electrode, N is the number of electrons that are transferred per molecule in the reaction. This is a key factor in determining the potential. F is Faraday's constant, which is 95,500 coulombs per mole. This constant represents the charge of 1 mole of electron. It is used to convert between the energy of the electron and the voltage in the reaction. Q is reaction coefficient. Q is the ratio of the concentration of the product to the reaction in the electrochemical reaction, to the reactant, in the electrochemical reaction at a given moment. It indicates the direction in which the reaction is proceeding for a general reaction of the type. Understanding the Nernst equation is in potentiometry. The Nernst equation shows that the potential measured by an electrode is not only dependent on the standard electrode potential, but also on temperature, number of electrons involved in the reaction, and the concentration of the reactants and products in the solution. In potentiometry, we measure the Nernst equation to relate the potential measured by the electrode to the concentration of ions in the solution. By knowing the standard potential and measuring E, we can determine the unknown concentration of ions in the solution. The logarithm relationship. The equation includes a logarithmic term, indicating that the relationship between the potential and the concentration is logarithmic. This means that small changes in concentration can lead to significant change in potential, as we said. Temperature dependence. The equation shows that the temperature plays a crucial role in determining potential, as higher temperature can increase the kinetic energy of particles, thus affecting the potential. Thank you. Thank you for listening.